Section 2.2, talking about these limits and limit laws. We have a lot more to discuss. So we'll call this, we'll just call it Section 2.2 Continued. Okay, Section 2.2 Continued. And just a little bit of a preview. We're going to continue to figure out how to find the limit. We're still looking at how to find the limit, remembering that the limit is the vertical value or the y value of the graph or the curve at a given x amount. And there's a lot of ways to doing it, so there's many ways. Okay, we can find the limit by looking at a graph. Okay, and that's usually a really nice way to find the limit, is by looking at a graph, if it's a nice graph. And we do this most frequently on the calculator, or use that calculator to confirm what you think the graph of the function is supposed to look like. We also can come in here, we're going to do this a little bit today in this recording, by looking at a table of values. This will be also on the calculator. And you will find that this is not really very fun to use the calculator and do this. But we will, because it kind of gives you a different perspective, but we won't do this very much. Okay, so not a huge emphasis on that, but we do need to look at it. We also will use what we call limit laws. There's a bunch of laws that we can use to play around with the function to come up with the value of the limit. Again, these are not difficult. You will find this to be very comfortable. The way to find the limit that you will like the most is by using direct substitution. And in the perfect world, we do this every time. But in reality, direct substitution is usually going to present us in a situation where the denominator is 0, so we don't get to use this very much because they're going to want to make it a little more challenging. We will do a lot of algebraic manipulation. Meaning they give me the function, they tell me to come up with the limit, I cannot use direct substitution, and so I start kind of doing these interesting things to the function, factoring, reducing, rationalizing, all these different algebraic methods I can use to kind of alter the function so that then I can plug the number in and not have a 0 in the denominator. And then we also have an interesting one which is called the Squeeze Theorem. This is kind of fun. Okay, the Squeeze Theorem. It's going to look very complex, but it's not. It's a very simple concept. And when they ask you questions, it's not going to be difficult. It's going to be pretty straightforward. They're going to give you a lot of information to work with. So it's called the Squeeze Theorem. This textbook, I think, calls it something a little different. Let me see what they call it real quick. Close to the Sandwich Theorem. That's what they call it. We always call it the Squeeze Theorem, but it can also be referred to as the Sandwich Theorem. So it sounds really weird. So those are several ways of finding the limit. And we'll look at all of these ways, we'll do examples of all these ways, and then when you have a question given to you, you're going to have to kind of figure out which one of these methods do I use. And you might use more than one method in order to come up with the result and feel confident that you have the right result. Now, in continuing this from the lecture which we had on Thursday, we would now be coming into Part C. Okay, if you really look back at your notes, this would be Part C if we wanted to try to keep these notes kind of working in order. So we're going to start off in Part C by determining the limit given a graph. And we've played a little bit with this, so we're going to take it a little bit deeper and make certain that we're really confident in understanding the value of a limit when given a graph. Okay, so I'm going to start here with an example. And I'm going to sketch a rough draft of a graph. And suppose this is height 2, and this is 1. And suppose this is what your graph looks like. Okay, and of course the limit is going to be asked at where the hole in the graph is, where there's something unusual with the graph. So the question would be, what is the limit of this function? And I don't know, let's call this f of x. What is the limit of this function, this graph? What is the y value of this graph when x is approaching a value of 1? Well, when x is approaching a value of 1, from the left, we're coming to a height of approximately 2. And from the right, we're coming to a height of 2. But notice the function doesn't even exist in x value 1 because it's an open circle. Well, when you work with the limit, it's kind of like making projections. You know, kind of like companies go out there and they hire statisticians to come in and project how their company is going to be doing in the next 6 months. So we don't really want to know for certain what exactly is happening at the x value of 2, but we're going to project what's supposed to be happening at the height when the x value is 2. So even though there's a hole in the graph here, the function is not defined here, the limit is equal to 2, because that's what it looks like it should be. Okay, that's what it looks like it should be. So the function does not even have to be defined there. Doesn't matter. We just kind of blind ourselves at the exact point and look at it as we approach it from the left and the right. So the limit can exist at the hole in the graph. Here's another one. Okay, very similar to that last one. Okay, and suppose this is g of x. So now we're going to say, what is the limit of g of x? So the question here is, what is the limit of g of x? And of course, they're going to ask me when x is approaching a value of 1, because that's where there's a little bit of confusion with the graph, where it's not so perfectly defined. And in this case, you can see that the function is defined in an x value of 1. The function value is actually this height of 1, because that's where the circle is filled. But I don't really care about that when I'm looking for the limit. I'm just trying to see where does it look like it's supposed to be going. So from the left, the height should be going up to a height of 2. From the right, the height is decreasing to a value of 2. So regardless of the function value, where it looks like it's supposed to be going is to a height still of 2. So the value is still 2 at the hole in the graph. Okay, and then actually this was simpler than the others. Okay, suppose your graph has no issues. There's no hole in it. There's no break in it. It's just a nice, pretty, continuous, normal graph, the kind that we like. Then it would be very simple to say that the limit of this function, named h of x in this case, as x is approaching 1, the height is simply 2. So where it looks like it should be going, where we project it to be, what we think the height of the graph is supposed to be at that location is the answer, not necessarily what the function value is at that point. So try to remember the limit can exist at a hole in the graph. Even if the function value does not exist there, that is where the limit exists. Okay, now we have some examples of what would be what they call, the first one here, we're going to call it the identity function. Okay, and the identity function is f of x equaling x. Okay, that is the identity function. And if you graph the identity function, you go through the points 1, 1, 2, 2, 3, 3, 0, 0, negative 1, negative 1. And you have that perfect line who has the slope of 1, that 45-degree angle, just that really nice, probably one of the first graphs you graphed years back, and there it is. So the function is f of x equaling x. So let's just kind of get some ideas here. So if they ask me, what is the limit of this function as x is approaching 1, what would it be? 1. Very good. Suppose they ask, what is this limit of the function as x is approaching 2, what would it be? 2. The limit of this function, let's go negative, as x approaches a negative 3. Ooh, I didn't fit this in here. Negative 3. So, can I say that the limit of f of x as x is approaching some number a, instead of the numbers 1, 2, and negative 3, if it's approaching a, what is this answer? It equals a, because it's an identity function. So the x value and the y value are the same on every point on the graph. The name of this ordered pair is 1, 1. This is 2, 2. This is 3, 3. So the x and y values are the same on the identity function. So the limit as x approaches a, as the x value is a, the y value will also be a. So this is a standard when you're working with the, quote, identity function. Okay. Now, this is the exact same question. What is the limit as x approaches a of x? This is the same question, because what does f of x equal? Am I off the screen? Okay. This is the exact same question. F of x is x. That is the function value. So this is the same question. So if you see it written this way, the answer is still A. It is the same exact question. One is using function notation, f of x, and the other is actually using the function value, x. Okay, so both of these are asking the same question, giving the same result. Okay, so let's try another one. Okay, we're going to kind of look at an example of a constant function. We'll call this g of x. Suppose it equals 5. Well, the way this graph looks, it's a horizontal value of 5. 1, 2, 3. I'm too high. Let's go 1, 2, 3, 4, 5 right there. It's a horizontal line. So then, if you ask these questions, what is the limit as x is approaching 0 of g of x? What does it equal? 5, the height of the graph. Right here, how high is the graph? It's up 5 units when the x value is 0. What is the limit of this function as, say, x is approaching 3? Up here, you're still at a height of 5. So remember, the limit is the vertical value, the height of the function. So we could do this all day. The limit of this function as x is approaching negative 100 is going to be 5. So we can make a conclusion from this, that the limit of g of x is, as x approaches any number, in this case, is going to be 5, because this is called a constant function. This is referred to as a constant function. It is equal to a constant. It is equal to a number. Now, see if this makes sense. Suppose it didn't equal 5, if it equaled 10 or it equaled 2 or something, it's still going to be a horizontal line. So suppose they say the limit of not g of x, but the limit of k, which would be saying something like g of x equals k, right? That's the same thing. As x is approaching some x value, do you know what this would equal? K again. So it'd be like saying g of x equals k. So if you have a constant function, the limit is just really simple. It's equal to the constant, which would be the constant height of the graph. So try not to make that difficult. Sometimes that takes a little, and it's not the concept. I know you can comprehend the concept. It's all this lovely a's and k's and x's and g of x's. It's just trying to get a handle on the notation, because I know you understand the height of that graph is always going to be 5 or some constant k. Okay, so now let's play around. Let's change and let this be part D. Okay, so we kind of looked at finding the limit of a function given a graph. We looked at a couple of special cases, which was identity function and a constant. And now we're going to talk about when is the limit possibly undefined. Okay, so let's take a look at where the limit is undefined. The limit is often undefined at a break in the graph, which some people call a jump. A break or a jump in the graph is where you're going to see the limit becoming non-existent or undefined. Here's an example of that. Okay, suppose your graph, so it's a little hard, okay. Suppose your graph looks like this and it has a hole, and then it picks it back up and goes the other direction. Okay, and we'll name this one. Why don't we name this h of x, just a variation to get off of the f of x. Then, of course, they're going to ask the limit at what x value? At 0, because that's where there's a problem. The limit's great. The height of the function is no issue anywhere else. But at 0, we're going to have an issue. So the limit of the function, whose name is h of x, as x is approaching 0, is asking the height. Well, from the left, it looks like it's a height of 1. From the right, it's a height of 2. So right here, we don't know what's going on. We cannot make a projection because it's doing different things from the left and the right. So this is, it does not exist. I write D and E does not exist. Because there's a jump. There's no consistency. It's not staying standard. It's not looking continuous or smooth. Okay, another place where there are issues are at a vertical asymptote. Okay, this means a vertical asymptote. Okay, and we've discussed this a little bit already. And there are a lot of vertical asymptotes we're going to run into. So here's a function, and note that it will also have a 0 value. It's going to be going through the point 0, 0. This is really defined as a piecewise function. It's defined as 1 over x everywhere except at x equaling 0, and then at x equaling 0 it's defined equal to 0. So, I don't know, name this one g of x. So if they ask me the limit of g of x as x is approaching 0, from the left it's headed to negative infinity. From the right it's headed to positive infinity. I'm trying to figure out where it looks like it should be going. And since it's going in opposite directions, I cannot make a solid projection. So here it does not exist. Now this last one, I would not ask you a question like this on a test. You'll see some of it in the book, and they might get pretty deep into it. We're not going to do this. You won't be tested on this. But this is where the graph is oscillating very quickly, okay? And it's kind of hard for me to graph it for you, but it would look something like maybe all is well to this point, and then all of a sudden it starts doing this crazy oscillating up and down, out of control. Okay, really oscillating very, very, very quickly. And so it's oscillating, it's vibrating, or it's oscillating so quickly that it's hard to tell what it's doing. So if you see something like this going on, and they ask for the limit of this function, maybe it's r of x, as x is approaching 0, we really cannot make a prediction because the function is going wild, and so we say this also does not exist. And here's kind of a picture of it in the book, if you want to see it, the way it's described in the textbook, right here. They just start using these dashed lines, and they say this graph is just, going crazy. It's oscillating very quickly as it gets close to 0, and they start using the dashed lines to try to represent it moving a lot in that region. Not just 2 or 3 times, but hundreds of times in a very small horizontal region. Okay, again, you're not going to see this on a test. I wouldn't test you on that. Okay, so now we've looked at it from a graph, from several graphs. Now let's talk about the limit using a table of values. Okay, find the limit using a table. And we're going to pick up the calculator. I'll show you the calculator on the screen. And I'll show you probably some tricks you already know with the use of a calculator. But suppose they're going to ask me to find the limit of a function as x is approaching the value of 1. And suppose that function is x squared minus 1 over x minus 1. Okay. Now, off to the side, they really could have just said f of x equals x squared minus 1 over x minus 1. And so they could have just asked this and not repeated it. But again, they can put the name of the function notation version of the function, or they can actually put the function value in the way they write the question for the limit. Okay? So what in the world does this thing look like? We're going to go to the calculator, and we're going to create a table. And in the table, we're going to put x values close to 1 from the right and from the left. So if we go in from the left side of 1, 0.9 is close to 1. Then if I want to get a little closer to 1, I might say 0.99. Getting a little closer to 1, 0.999. I'm getting really close. Hold on, that's not right. Yeah, that is right. Okay. Getting really close to 1. But I'm not going to try to do it at 1 itself, because at 1 it's undefined, because the 0 is in the denominator if I put an x value of 1 in. That's getting close to 1 from the left. To get close to 1 from the right, I might look at what, 1.001 or 1.01 or 1.1. Okay, so that's kind of closing into 1 from an x value to the left of 1 and closing in from the right. So we're coming from the left and coming from the right, approaching the value of 1, but not plugging 1 in because it makes the function undefined. So we're going to play with this on the calculator. So when you go onto the calculator and you go to your y screen, we're going to write x squared. We're going to type x squared minus 1 divided by x minus 1. And so I'm going to pull the calculator up on the screen. We're going to lose these notes when I do this. Oh, I might can show both of them. Nope, I can't. Well, maybe I could. No, I can't. Well, let me minimize the screen. I can make this happen. Okay, so you hit the y equals button and it brings up here. You put in your parentheses and you type in x squared minus 1 divided by, and be certain you have parentheses, x minus 1. And now, well, I didn't get it in there. Typed it too quickly and it runs kind of slow with this little package. X minus 1. Close. There it is. And I made a mess over here, so I'm going to get rid of this. Okay, get back over here. Okay, so there it is. Okay, you can see it, and here is the table. Well, these tables are 0, 1, 2, 3, 4. These are just integers. This is not small enough. I need these little bitty numbers, okay, that I have. These are the numbers I want in my table. So your table, right here in blue, I'm going to go second table, and it'll show on my screen this little window. And I need to change those values. So you have a table set option up here. So I'm going to go second table set. And if I come down here to the independent variable, which is x, and I select, I've got to move the screen. I move it to the ask question, hit enter, so that I've selected ask. That'll give me the choice to put the x values into the table myself. So you move your cursor over to ask, and then hit enter, and then go back to your table, and it's waiting for you to put such as these numbers into the table. Okay, so it's giving you control of the x values you put in the table. So the first x value I want is 0.9, and I hit enter, and it will calculate it for me. The next number I might want to put in is 0.99 and hit enter, and it gives me a 1.99 result. The next number I might want to put in is 0.999. Remember, I'm getting closer and closer to 1 from the left side, and then it comes up. So where does it look like it's headed? Where's the y value going? Looks like it's headed to 2, unless there's a jump in the graph or something wild with the graph. So it looks like it should be going to the value of 2, but there might be something weird happening. So now I'm going to come in from the right side and put in the 1.001. That's not too bad. We're still playing with the number 2, right? And then I put in the 1.01, and then the 1.1. Okay. So it definitely looks like there's nothing crazy. It doesn't look like, well, really there's a hole in the graph at this point, but it does. It should be going to a height of 2. So right here, if I want to play around and put 1 in, which I have squared off, the one we're really not supposed to ever put in there, that doesn't make it happy, okay? We get an error because it cannot calculate that because that's where it's undefined. So we can tell by the table of values that it should be about 2. There's probably a hole in the graph right there, and there is a hole in the graph right there, but the answer to the limit is a height of 2. So this is really nice. This is not fun if you can't remember how to tell the calculator to put it on ask. Okay, you'll be totally lost. So be certain you remember under the table set, we go to table set and put this independent value on ask, so it gives you the ability to put whatever x value you want in here. If not, you're not going to be able to accomplish this lovely task. Okay, so be certain you remember to do that. Also be certain to remember to take it and put it back on auto at some point, because we're through with this question, because it'll drive you crazy trying to figure out why isn't it generating values for me. Okay, so just a few tips with using your calculator. Okay, so we've come to the conclusion that this should be 2. Okay, using the table, so this answer is, by using that table, a value of 2. Okay, probably wouldn't have hurt for us to have actually written those values in. Could have done that. Where did they go? Oh, it's not going to be there anymore because I've changed it to auto. Okay. All right, so that's how you kind of play with the table. It's not necessarily fun, okay, but it's possible. So let's do it one more time. Let's do another example. They're going to ask you to do some of this in your homework. It's trying to, again, help you to find a vision of what the goal is here. To find the height of the function, meaning the limit at a certain value. Now, another one we know about is this one. Suppose they ask me the limit of 1 over x as x is approaching 0, meaning the function is defined as 1 over x. And we know what that function looks like. Okay, we know it has a vertical asymptote at 0, and this is not going to be a good situation. Okay, so before we pick up our calculator, we already know. Okay, we already know this. We really already know the answer, but we're going to show what the calculator is going to do. We know that this graph is looking like this, and then an x value of 2, this thing is going to be undefined because the left side and the right side, one's headed to positive infinity, one's headed to negative infinity. This is not going to work. This sucker is going to be undefined. But we're going to prove it, or we're going to show it by using the table, again, to try to get you a little more comfortable with using the table. So find this limit using table values. We already know the answer, but we're going to watch the calculator kind of reinforce what we know to be the answer. So we're going to go onto the calculator and we're going to put the function value of 1 over x in. Then we're going to create a table. We're going to put the table set on ask rather than auto. We're going to look at values where x is approaching 0. So from the left, like a negative 0.1, a negative 1/10. And getting closer would be a negative 100th. And getting closer would be a negative 1/1000th. I mean, you could get really crazy with this, okay? You go this far. This is coming in from the left side. If we're going to come in from the right side, we might start at a positive 1/10th, then a 100th, then a 1,000th, then a 1/10,000th, trying to come in from the right side to the value of 0. So these are the numbers we can use to get a projection or try to see. Actually, we're going to see that they're not coming together at all. So we'll go into the calculator and play with this one. So come in here and go to your y equals. Change this to 1 over x. See if I can get everything up here. Okay, change this to 1 over x. Go to your table set, and that's not hitting the second, table set, there it is. Come down here and switch it to ask. Then go to your table, second table, and it's waiting for you to put these table values in. So you'll say a negative 0.1. And we get a height of negative 10. Put a negative 0.01 and get a height of, wow, a negative 100. It's falling fast. A negative 0.001, negative 1,000, and negative 0.0001. So it's growing, it's going negative very, very fast. And so this is that negative infinity side of the graph. Now, suppose we want to go the positive side. We're going to do the 0.001, actually 3 zeros and a 1. And this should be a very large positive number, positive 10,000. 0.001, 0.01, and 0.1. Okay? So right here is where 0 is. It's between these two numbers. Okay, and you can see that from the left we're extremely negative and from the right we're extremely positive. which from our graph makes perfect sense. From the left, we're coming down here to some very big negative numbers, like a negative 10,000, and from the right, a positive 10,000. So this doesn't work. So we're not coming to agreement on the left and right side, so this does not exist. The limit does not exist when x is 0. And so you can kind of see what the table of values looks like, because you might not be able to predict the way the graph looks, and kind of have an understanding now of using the table to come up with those limits. Okay, there is one in the textbook, which I'm going to show you real quick, which tells you that sometimes tables are just not the way to go. Okay, it's kind of nice, but sometimes it just doesn't work at all. I'm going to look at example 8 on page 51 of our textbook. Okay, and we're going to actually play with functions similar to this right here. They're asking for the limit as x is approaching 0. And of course, that puts a 0 in the denominator of the rational function, which is going to be an issue. So look at these values they're looking at. Wow, 0.0005, like 6 zeros in front of the one on the left, both sides. And they bring up a table, okay, and they come up and put all these values in the table, and it just doesn't give them a good projection. It looks like maybe you're going to 0.05 on one side, and maybe you're headed towards 0 on the other, and you're getting these, you're throwing in really small numbers, but it's not giving you good results. And so it says using a computer or a calculator may give ambiguous results, as in this example. And we cannot substitute x equaling 0 into it because it becomes a 0 in the denominator. So sometimes it doesn't really work. Okay, sometimes we just can't get it to fall for us when the functions get very complex. So it's not always a perfect. None of these methods seem, you've got to pick the right method for the question, and you'll get good at this over time. So don't get overly frustrated on something like this. Know that sometimes it doesn't work as perfectly as we want it to work. Okay, so now we're going to shift gears. We've taken a look at finding the limit when we have a nice graph, but usually there's a hole in the graph or a jump in the graph or whatever. Then we've looked at doing it when you've used a table to try to find the limit. Now we're going to look at it by using limit laws. And these are really easy. And what this will do for us is break a very complex graph down into something simple so you can visualize the graph, and then you can calculate the limit very easily by calculating it really in parts. So we have all these lovely limit laws on page 49 of our textbook, and I will write some of them down for you, especially to help give you an idea of what they really mean. So if you look at page 49 of your textbook, it'll show you all these limit laws. Okay, there they are. Okay, so it says if you have the limit, you have two graphs here. You have an f of x graph and you have a g of x graph. And so if you're looking at when the x value is approaching c on both of these graphs, if the height of your f graph is L when x is c, and the height of the g graph is M when x is c, then you come up with all these lovely results. Okay, so this does make sense. So let me see if I can show you how the first one makes sense and see how easy this really is to apply. So we're going to go ahead and assume by that the limit of f of x as x is approaching some x value, say c, equals L, and the limit of g of x as x is approaching some height or some x value of c is M. Okay, given this, if they want to ask me what is the limit of f of x plus g of x as x is approaching a value of c, that's easy to do because the limit law says this is equal to the limit of f of x as x is approaching c plus the limit of g of x as x is approaching c. So you can split it up. If you have a sum of two functions, you can split it up and do individual limits. And then you know the limit of f of x was given to be L. The limit of g of x was given to be M. And so the answer is simply L plus M. Okay, it's that simple. Okay, you just add the heights of the graphs together. Then they have a second limit which says if you have a constant times your function, a number like k times f of x as x is approaching c. K is a number, 2, 3, 5, 7. It's just a number, a constant. This is equal to k times the limit of f of x as x is approaching c, which equals k times the value of that limit, which is L, so it's just simply k times L. Okay, so now you can look at these rules, these limit laws, and they're very logical. There's nothing tricky here. They're really quite logical. So we did the quotient, we did the constant. It works for the difference. If you're subtracting two functions, then you're going to subtract each function individually. So it'd be L minus M. They're skipping the middle step. Okay, so if you're subtracting, you can find the limit of the first minus the limit of the second. The product, you can find the limit of the first times the limit of the second. The quotient, find the limit of the numerator over the limit of the denominator. And I'm going to do the power rule and the root rule and describe it a little more thoroughly here. Okay, this is the power rule. The power rule says if you're taking the limit of f of x to a power, like the exponent of n, okay, as x is approaching c, you can rewrite this as the limit of f of x as x is approaching c and just find that limit and then take this whole result to that exponent. So you can break it down, and we'll do some examples which will make this make sense also. So this equals the limit of f of x as x is approaching c was given to me to equal L, so this is L to the power of n. And then the last one that I wanted to put some emphasis, there's a bunch of them there, I'm just kind of putting emphasis on a few of these, is your root limit. And it says if you're taking the limit as x is approaching some number, say of the square root or the cube root or the fourth root of f of x, a square root function or a root function, then this can be redefined as the limit of f of x as x is approaching c. And when you find that answer, you take the nth root of it. Okay? Take the nth root of the value of the limit. So this then becomes the nth root of L. Now, this seems kind of silly, but this really becomes handy and nice and easy. You're going to really like these homework questions because there's no major challenge involved here. It's going to be very easy for you to do. So let's go in and do some examples of applying this. Okay. Actually, I've forgotten a couple. Let me do a couple more. This is not in that blue box. And this is something we've already talked about, but this is just a little bit of a reminder. Okay, remember that if you take the limit of a constant as x is approaching a number, like the limit of 5, this is the horizontal line, this equaled the constant itself. Or if you're taking the limit of x, this is the identity function, this is the identity function, then that equals the constant itself. Okay, those are the two. One of them, this is the identity function, and this one was the constant function. So that's just a little bit of a reminder, and that's in a different blue box in this book, I think on the, oh, I don't know where they put it. Somewhere. I can't find it, but it should be in the book, but they're not putting it in the same box. Okay, so now let's go in and take a look at some examples. Part A. Suppose they ask me, what is the limit as x is approaching 3 of this function, 4x squared minus 5x plus 7? We can evaluate this very easily, but you're just kind of practicing the method so you can apply it to something hard. Yes? I sure can. Thank you for telling me to do that. I should have been thinking all along. That's much better, isn't it? Okay. Okay. So this is going to be, this would be like f of x and g of x and h of x. the sum of three functions. So we're going to break it up. So we're going to rewrite this as the limit as x is approaching 3 of 4x squared minus the limit as x is approaching 3 of a 5x plus the limit as x is approaching 3 of 7. So this would be the sum and difference limit law where you split it into parts. And this is like three functions, f of x, g of x, and h of x, where you split it up. Now another one of our limits laws, so if you had a constant, you could put the constant in front of the limit. So we're going to move the constant to the front of the limit. So this can be rewritten the limit 4 times the limit of just x squared as x is approaching 3 minus 5 times the limit of x as x is approaching 3. And then the last one is our constant function. Okay, so we pulled the constant out front, which was the constant multiple rule, okay, one of the limit laws. Okay, so now we have one being squared. So now we can say this is 4 times the limit of x as x is approaching 3, all squared. Okay, so now we have used every possible limit law that can be applied, okay, to this particular function. Give y'all a minute to catch up. If I get too far ahead of you, don't hesitate to say something. Okay. So now, let's look inside this little square bracketed area. What is the limit of x as x is approaching 3? This is the identity function right here, right? The limit as x is approaching the constant is the constant itself. So visualize the identity function where every point is 1, 1, 2, 2, 3, 3, 4, 4. So this one equals 3. Here's the identity function again. What is the limit of x as x is approaching 3? It is also 3. And what's the limit of this one is the constant function, where the horizontal graph where y equals 7. So no matter what x is approaching, the height of the graph is always 7. Okay? So this is your constant function, this is your identity function, and this is your identity function. So we broke down this complex equation into strictly finding limits of the identity function and the constant function. So this is simply 4 times 9 minus 15 plus 7, which is 36 minus 15, which is what, 21, plus 7, which gives me a grand answer of 28 by applying all limit laws. So your limit laws take a complex function and break it down to really strictly your constant function, your identity function, to make it very easy to make the computation. And this is applying all of the limit laws, and they're going to want you to do this step by step. Very easy. Okay? Very easy. We'll do another one just to make certain you're good at this. Suppose we want to take the limit of 3x squared minus 5. It's a quotient over 2x plus 7 as x is approaching 2. So it's a quotient. So by the quotient law, I should be able to take the limit of the top divided by the limit of the bottom. And you're hearing me say the limit of, the limit of. Really, I said the limit of as x is approaching 2. The limit of as x is approaching 2. Okay, so you need to remember this x approaching 2 is like really important piece of information that we can't just let fall. It has to carry with us. So by the limit laws, this is the limit of the numerator as x is approaching 2. And don't forget to write that as x is approaching 2 over the limit of the denominator as x is approaching 2. Then in the numerator, you can split this up. This would be like f of x, and this would be like g of x. So the numerator can be rewritten as the limit as x approaching 2 of 3x squared minus the limit as x is approaching 2 of 5. Splitting it up. And the denominator the same way. The limit as x is approaching 2 of 2x plus the limit as x is approaching 2 of 7. Now the limit of the 5 and the limit of the 7, we already know those answers. They're 5 and 7. We're there. We're all the way down to the constant function. But these first two need a little more work. So we can bring the constant, the 3 out front of the limit and the 2 out front of the limit. So the numerator is now 3 times the limit of x squared as x, bless you, is approaching 2. The second limit, we can't do anything more to it. It's broken down as far as we can make it go. And then the bottom, pull the 2 out front. We have almost broken this down as far as it will go. There's one more thing we can do. Go ahead and write that. I guess I should dot all these lovely I's. So what's the one additional limit law that I can apply? The x squared, the x1. That's the only one left. Right here, this squared. I can break this down one more time so I take it all the way down to the identity function. So I'm strictly working here and the rest of it is being copy-pasted. So this is going to be 3 times the limit of x as x approaches 2. Get that result and get that number and then square it. My LIM is getting sloppier and sloppier. Finally, okay, it takes time, but you can see it breaks it down to just the constant function or the identity function. What was an ugly rational, which we may not have been able to visualize? Actually, this is going to have an oblique asymptote. It would not have been a very pretty graph. Okay, but really, this has an oblique asymptote. This is not a pretty graph. It would be difficult to look at graphically and determine the result. So here we go. The answer is 3. What is the limit of x as x approaches 2? 2. So this is the 2 being squared because that's the identity function where every ordered pair is 2, 2, 3, 3, 4, 4, 5, 5. Okay. This is the horizontal line, horizontal at a height of 5. So when x is approaching 2, who cares what x value it's approaching? The height is 5. This is the identity function. So it'll be 2 again. And this is another horizontal line at the height of 7. So it is 7. So we get 3 times 4, which is 12 minus 5 over 4 plus 7, which is 7 over 11. That is the vertical value. Now I'm telling you, this is an ugly function if you were to graph it. Okay? It's not a pretty thing. But this, as long and tedious as this is, and as many times as we get sick of writing the word limit, that's a nice, easy answer. Okay, a nice, easy result. Okay, now I'm going to put another one up here that doesn't require so many steps. I'm going to pause the recording and have you work on it. You can talk amongst each other. Is that right? Part C? Yep. Okay. So I want you to use the limit laws to evaluate the limit of the square root of x squared plus 5x as x is approaching 4. So you're going to use the root, the limit root law, to apply this. And I guess I could give you the first step since I've not done an example. This is the same thing as the square root of the limit of x squared plus 5x. Now see if you can take it all the way to the answer. Let's go in here and make it happen. Okay, so we can break this down as to the sum of two functions. So it can be the big square root of the limit of x squared, don't forget, as x is approaching a value of 4, plus the limit of 5x as x is approaching the value of 4. This first one is the power rule, where the exponent can be on the outside. This is going to get really weird looking. Big square root, and this is the limit as x is approaching 4 of x, and that's a number that we're going to square. And this one, the constant can come in the front, 5 times the limit of x as x is approaching 4. So these are both the identity function. So this is the square root of something squared. The limit as x is approaching 4 of the identity function is 4. And this is the limit as x is approaching 4 of x, again, is the identity function. So we have the square root of 16 plus 20, which is the square root of 36, which is 6. Very good. Okay. Very good. Okay, so then you're going to love this next section, because this is like the really easy part. This is the part which would always happen, which is finding the limit by direct substitution. In fact, this is what we really always try. Yes?
On the square root, you had a good point. How do you know if it's positive or negative?
If they give you a plus minus, it's what they give you. If they give you a plus minus in front of the radical, then you keep a plus minus. If they don't give you the plus minus, you assume it's only positive. Okay, and that's kind of just the standard notation. I know it's always kind of iffy. If you are taking the square root of a number, if you have x squared equals 36 and no one gave you a radical, but you put in the radical, if you create the radical, then you create this. You see how that kind of works? Okay, so when you put the radical in place, you put the plus minus. But if they give you a radical and only there's no sign in front of it, then you assume the positive. Okay, good question. Okay, limit by direct substitution. You're going to love this. In fact, this is where we're going to end up going. We're going to always try direct substitution. And of course, most times there's going to be a major problem. We can't use it. But it's really what you want to do is direct substitution. So using direct substitution is quite easy. If you have a function that has no problems, it has no vertical asymptotes, it has no limit on its domain, it has no breaks, no jumps, it has no issues, it's just a nice pretty curve, then you're never going to have a problem with the limit. It's just that vertical value. So if you have a pretty curve, you just use direct substitution. And the way they put this is they say if, that's supposed to be an I, if f of x is, and we'll just put it in very informal terms, a nice curve with no issues. Okay, there's no jumps, there's no breaks, there's no vertical asymptotes, it's not doing anything off the wall, okay? Then we can just plug, then we consider it continuous, and then we just use direct substitution. Then plug in the value. Okay, now you realize this is seldom going to happen. Okay, in our wonderful world of homework, this is not going to happen, but we can wish for it to happen. So for instance, here would be an example. Suppose they ask me for the limit of the function x squared plus 2x minus 3 as x is approaching some number. Well, this is a parabola, right? This is a parabola. It's got it's concave up. It's down there at the vertex at 0, -3. It has no breaks. It has no holes in it. It has no vertical. It's just a nice, pretty continuous function. So I can just plug the 3 in. And so this would be what? 3 squared plus 2 times 3 minus 3, which is 9 plus 6 minus 3, which is 11. You just plug it in because it's a no-problem function. It's a nice, pretty function. Okay, so that's direct substitution. But suppose, 9 plus 6 is 15 minus 3 is 12. Thank you. All right. But then suppose they say, what is the limit as x is approaching a negative 5 of x squared over x minus 5? Boy, the minute you write the rational, you're thinking, okay, this is going to be one of those vertical asymptote examples. But if I plug in -5 in, is there a problem? No. Where's the problem? At 5. So there's one tiny little place in the graph. There's confusion. It's not at negative 5, it's at 5. So we can just plug it in. And this is a negative 5 squared over a negative 5 minus 5, which is 25 over a negative 10, which is a negative 5 halves. No issues because we weren't at the place where there's an issue. They didn't ask me at 5. They asked me at negative 5. Okay, suppose they give one like this. The limit, and often they'll use t. Okay, watch for the variable t. The limit as t approaches 0, and it's something like the square root of t squared minus 8 over t squared. Now, can I use direct substitution? No. Okay, can't do this one. Direct substitution does not work here. So we're going to have to look for another way to make it happen. We might have to graph it. We might have to use a table. We might have to use some algebraic manipulation. We got to look for another way. Okay. Suppose we have something like the limit as x is approaching 0 of 1 plus x plus sine of x over 3 cosine of x. I would not want to have to graph that. I have no clue what that looks like. But are we lucky enough to be able to plug this number in and all be well? Yeah, we're going to be okay. So let's plug it in. So this is 1 plus 0 plus the sine of 0 over 3 cosine of 0. So this is 1 plus 0 plus sine of 0 is 0 over 3 times cosine of 0, which is 1. So the height of that function when x is 0 is a third. The limit of that function, there's no hole in the graph or anything weird going on. When x is 0, it's a very simple outcome just using direct substitution. We will not be blessed to be able to plug it in like this very much, okay? They're not going to make it easy. They're going to want to give you the difficult situations. They're going to want to make you work at this. So this isn't going to happen very much. So enjoy it when you can. Okay, I'm going to have some more graph paper. We're really going through the paper today. Okay, so now part H, another method of finding the limit. Find the limit using algebraic manipulation. This, I think, is the most enjoyable, if you can ever call this enjoyable. Okay. Find the limit using algebraic manipulation. Okay, and we're going to start off by using a method or examples of factoring and canceling. So these are not bad. Okay, here's an example. Suppose you're asked to find the limit of this function, x squared minus 7x plus 10 over x minus 2, as x is approaching the value of 2. So your first thought is, please let me be able to use direct substitution, and then it doesn't work because the denominator is going to become 0. So the next option is, man, I hope this thing factors. That would be really nice. And so let's see if it factors. So we're going to find the limit as x is approaching 2, and that numerator will factor into an x minus 5 times an x minus 2. And isn't that just convenient? So at this point, we know that graphically, because I can cancel the x minus 2 binomials, there's a hole in this graph at an x value of 2. There's not a jump, but there's a hole there. So then I can just come in here and say, this is the limit as x is approaching 2 of x minus 5. And there's a hole in the graph at this point. But I can evaluate it now using direct substitution, which is 2 minus 5, which is a negative 3. So the height of the graph, even though there's a hole there, the prediction of the height of the graph at the hole is a height of negative 3. Now, here's another thing, is note where I stopped writing the word limit. I stopped writing the word limit whenever I put in, as soon as you substitute the value of 2 in, you no longer are writing the word limit. Okay, the minute you put the number 2 in for the x value, you don't write the word limit anymore. You're actually evaluating the value of the limit at that point. Okay, what if you have, and this is a really unusual variable to use, but they were using this in the book, so it's probably going to happen in my math lab. It's kind of weird to use y, but they're using y. That's really odd. Okay, the limit is y is approaching 0 of 5y cubed plus 8y squared over 3y to the 4th minus 16 y squared. I really prefer not to use the y variable, but they're probably going to do it in my math lab. Okay, if I put a 0 in, the denominator is 0, and this is not good. So I'm going to see if I can factor here and get some reduction. So you remember, you still have the limit here because I'm not using direct substitution. I'm just algebraically altering this rational function here. So I'm going to take a greatest common factor of y squared out of the numerator and a greatest common factor of y squared out of the denominator. Then the y squared factors will reduce out as a 1. And then could I use direct substitution by any chance? Does that fix the issue? Yes, that's kind of nice. Now I stop writing the word limit. I put the value of 0 in. 0 plus 8 over 0 minus 16. The height of that function looks like it should be at about a negative a half when the y value is 0. Okay. All right, let's see if y'all can remember how to factor a cube. Suppose we have the limit as x is approaching 2 of x cubed minus 8 over x to the 4th minus 16. This is really a review of your ability to factor. You're going to have to be able to factor or this isn't going to happen. How does that, well, this is still the limit. Don't forget to write the limit. How do you factor that x cubed minus 8? Close. No. No, that's not quite right. Anybody remember? What's that lovely little formula? Let me see. It's if you have a cubed minus b cubed, it is a minus b times a squared plus ab plus b squared. Do you remember that? Yeah. We've seen this at some point in our life, right? It was back in one of those little blue boxes in some textbook way back when. Okay. So this is going to be an x minus 2 times an x squared plus a 2x plus a 4, where you replace the a with x and the b with 2, because this is an x being perfectly cubed and a 2 being perfectly cubed. So everywhere there's an a, you put x, and everywhere there's a b, we put a 2. How about that denominator? That's a difference of squares, right? So this is going to be x squared plus 4 times x squared minus 4. Okay? Had it been, say, x squared minus 16, this would have been an x plus 4 times an x minus 4. But since it was an x to the 4th minus 16, it's an x squared plus 4 times an x squared minus 4. And this little guy right here, somebody better still do something because I still cannot plug in a value of 2. So something has to still happen. This can factor, right? Now we're talking. So I can't do anything more to the numerator. Even though that trinomial looks like it should factor, it's not going to. So this is an x plus 2, x minus 2. Now let's hope. I know, hope that's good enough, right? That's what we're thinking. Boy, I hope that fixes the problem. Does it? Can I put the 2 in now by direct substitution? Yeah, so there must have been a hole in the graph and an x value of 2. I don't have any clue what this thing looks like. Okay, so now I'm not writing the limit anymore because I'm putting numbers in. This is going to be 2 squared plus 2 times 2 plus 4 over 2 squared plus 4 times 2 plus 2. How about some order of operation on this sucker? What is this? It's a 4 plus 4 plus 4 on the top, and a 4 plus 4, which is 8, times 4, which is 32 on the bottom. Am I right? So is it 3/8? There it is. Okay, so that one was just really kind of pushing you a little bit to make certain you remember how to factor. Okay, remembering your abilities to factor. A lot of algebra happening here. Okay, and this was like kind of getting these organized. We talked about using algebraic manipulation. These were the examples of factoring and canceling. So down here, we're going to have examples. By multiplying times the conjugate. Okay, multiplying times the conjugate. So very briefly, y'all remember what the conjugate was? Remember, memories, remember, do we remember? Remember, if you have x plus 3, the conjugate is x minus 3. They're conjugates of one another. One's a plus and one's a minus. And what happens when you multiply something times its conjugate? There you go. You get a difference of squares. When you do FOIL to this, it becomes x squared minus 9. So the O and the I add out as 0, or they end up eliminating each other. Okay? We're going to have stuff like this. Suppose you have something like the square root of x plus 9 minus 5. That's a binomial. Its conjugate is going to be the square root of x plus 9 plus 5. Those are the conjugates of each other. All right? Those are conjugates of each other. So when you end up multiplying them, what do you get? Oops, that should be a parentheses. Anybody know what happened when you form the product? There you go. You square the first one, which removes the radical, and then the negative 5 times the positive 5 is a negative 25. So this becomes what, x minus 16? Okay, so we're going to be doing this kind of stuff. It's fun. It's all good. Okay, so we're going to put a little number A underneath here and make it, we're going to do this example and be ready for some algebra. Okay, take the limit as x is approaching 4 of, let's say, 4x minus x squared over 2 minus the square root of x. And it doesn't hurt to put a little hook on your radicals, especially when they start getting pretty big and complex. Okay, so can I put a 4 in? Nope. Right, gives me a 0 in the denominator, so I cannot use direct substitution. So what we're going to do is multiply by the conjugate of the binomial who has the radical. So this is going to be the limit as x is approaching 4 of 4x minus x squared over 2 minus the square root of x times, I'm going to multiply times the conjugate. The conjugate of that denominator is 2 plus the square root of x. But I have to multiply by something equivalent to 1, so I multiply times this 2 plus the square root of x over itself. So I'm really multiplying times something equivalent to 1. Okay, so this equals, and don't forget we're evaluating a limit, so you must be writing this word limit. This numerator is now 4x minus x squared times 2 plus the square root of x. And the denominator, if you do FOIL, F-O-I-L, 2 times 2 is 4. The outside 2 square root of x minus the inside 2 square root of x makes 0. And the last is a negative square root of x times, maybe I should do this. Okay, outside is 2 square root of x. Inside is a negative 2 square root of x. And last is the square root of x times the square root of x, which is x. That's FOIL. That's the whole distribution of the binomial times the binomial. So this is the limit as x is approaching 4 of 4x minus x squared times 2 plus the square root of x over 4, these terms 0 out, minus x. Now, can I plug in the 4? No, well, that's the pits. Where's he? Move on. Get that out of there. Okay. Any suggestions? There we go. Let's try a little bit of factorization right here. Okay. If this binomial, if I take an x out, it's going to leave behind a 4 minus x. And isn't that nice? There you go. Okay, so you kind of have to look ahead, especially like you did in trig. You kind of, where in the world is this going when you were doing identities? So this is x times 2 plus the square root of x. Now when I substitute the 4 in, I no longer write the word limit. This becomes 4 times 2 plus the square root of 4, which is 4 times 2 plus 2, which is 4 times 4, which gives me an answer of 16, which means the vertical height of this graph at an x value of 4 should be about 16. There might be a hole in the graph at that point, which there is because of this cancellation. But that's what the vertical height of the graph would be. So that's a little bit of algebraic manipulating. Now let's do another one. This is going to be a little more difficult. Suppose we want to know the limit as x approaches 1 of x minus 1 over the square root of x plus 3 minus 2. The first thought is, can I use direct substitution? No. Too bad. Okay, so then I got to figure out what in the world am I going to do with this mess. So I'm going to try the conjugate of the denominator again and just hope it works. Okay, we don't really know if it's going to work or not, but it pretty much is our only option. This gives us something we can do. So this is an x minus 1 over the square root of x plus 3 minus 2. The conjugate of that denominator is the square root of x plus 3 plus 2. Okay, so what does this turn out to be? This is the limit as x is approaching 1. I'm just going to write the whole numerator. I'm not going to change it. I'm just going to leave it alone for a few minutes. Later I might have to factor, you never know. This denominator is where it's getting ready to get fun. Okay, FOIL. The square root of x plus 3 times the square root of x plus 3 is x plus 3. Outside is 2 times the square root of x plus 3. Inside is a negative 2 times the square root of x plus 3. And last is a negative 2 times a positive 2, which is a negative 4. FOIL, the FOIL method. Okay, I'm not going to change the numerator. I'm going to leave it alone. At some point, I might have to do something with it, but for now, I'm going to leave it alone and hope that something would cancel. So this denominator is now x plus 3. These two guys zero out. X plus 3 minus 4, which good, is x minus 1. Which is what we kind of wanted to have happen. And they do try to write these questions so that this will happen. These will now cancel. And can I use direct substitution? Yes, I can. So this is 1 plus 3 plus 2, which is the square root of 4, which is 2 plus 2, is a height of 4. Again, I have no idea what this graph looks like. I would not enjoy working with it on a table either. So even though this might not be fun, it gives us a nice result. Okay, I hope I can fit this next one on this piece of paper. And I think I can. Okay, I'm kind of low on the page. This is the last one like this. Suppose we take the limit as x is approaching negative 1 of the square root of x squared plus 8 minus 3 over x plus 1. If I put a negative 1 in, the denominator is 0, which gives me an undefined situation. Here, notice the radical is in the numerator. So you're going to look at the conjugate of the numerator to kind of work here. I'm going to start it for you, then I'm going to pause the recording and see if your algebra is strong enough to get through this. Okay, I'm going to give you the first step. Okay, which is to multiply times the conjugate of the numerator. And feel free to talk to each other. Okay, let's take a look at it. If you do FOIL to the top, the square root times the square root is no more a root. Your O and your I cancel, and the negative 3 times the positive 3 is a minus 9. Ooh, I didn't make that big enough. Oh, I didn't get that big enough. Oh, well. Okay. So this is what? X squared minus 1 over x plus 1. I'll make it, I won't be quiet, so x squared plus 8 plus 3. Oh, it's going to be close for me to fit it on this page. Okay, so now it's the limit as x is approaching negative 1. This factors into an x plus 1, x minus 1. These guys go. If I put a negative 1 in the numerator, oh, I don't need to write this again. The numerator is a negative 1 minus 1, which is a negative 2, and the denominator, negative 1 squared is 1, and 1 plus 8 is 9, so it's the square root of 9 plus 3. Did y'all get this right? So this is a negative 2, 6, which, yes, is a negative 1/3. Very, very good. Very good. So let's pause it and let y'all take a break. Who wants to go through this twice? Okay, so let's go in here now. It's an hour and 37 minutes so far recording. And let's finish this. I'm glad it paused while we took a break without just giving up on us. And we should be moving into part I. all right, which is really nicely finally the last part of this section. And this part I, as we're continuing to find ways to calculate the limit, is to find the limit using the squeeze theorem. Are y'all arguing that I'm doing it out of place? You can't even see if I'm moving along. Okay. So I call this the squeeze theorem, but this book is referring to this as the sandwich theorem. I think the squeeze is a better description of it all. And just trying to give you a little bit of a warm up to this thing. If we say that g of x is less than h of x, then we can also say that the limit as x approaches a of g of x will be less than the limit as x approaches a of h of x. So if g of x is smaller than h of x, then it would be logical that the limit of g of x would be less than the limit of h of x. So trying to get, and this is where the visual or graphical kind of view of this will make it much more understandable. So if you visualize this g of x and h of x, if g of x is smaller than h of x, suppose our g of x function looks like this, and suppose our h of x function looks like this, so that g of x is always smaller than h of x. Well, if that's the case, then if you were looking for the limit, say here at 1, if g of x is always less than h of x or under h of x, then it would make sense that the limit would be less than h of x also. Okay, so it's a logical. I mean, this is a lot of notation. Here's a visual of how in the world and why in the world this works. When you actually get to the theorem itself, which is on page 53 of the book, okay, it's going to read something like this. And then I'll pull it up. So I'm going to kind of give a real informal, because it's going to be very wordy. But it's going to go la, 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 la. And then it'll say if g of x is less than or equal to f of x, which is less than or equal to h of x, and the limit of g of x as x approaches some number a is less than or equal to the limit of h of x as x is approaching some a, kind of like this up here. Then, and if these two things equal L, okay, if the limit of g of x as x approaches a, hold on, I don't want to do it, I'm saying it wrong. Let's change it. If the limit of g of x equals the limit of h of x, which equals L, so if their limits are the same, their heights are the same, okay, this would be this situation. Suppose g of x looks like this, and h of x looks like this, and they touch right here. Okay, so that at this point A, these two, their limits are the same, and that height is a height of L. If their limits equal, then we can say that the limit of f of x as x approaches A is also L. Okay. Write that down. I'll give you a minute to get it written down, and then I'll explain it a little bit more. The screen or the whole, like this? Oh, yeah, okay. There you go. Okay, once you get that written, if f of x is between g of x and h of x, that's what this string right here tells me. If f of x is between g of x and h of x, okay, this is g of x, and this is h of x. So f of x is in here doing something, but it's always between them. That's what this means. F of x is between them. Well, if the limit of g of x equals the limit of h of x at some value, then f of x is going to have to equal that same value too if it is between them. Okay? So if it is between them, it's getting kind of crushed between them so that they all are trapped at this height, when the x value is, say, 1, which in this case is a. So it's squeezing it between them, which gives us then the limit of the function who is trapped between the g of x and the h of x having to have that same value. So it's kind of a messy vision, but that's it. And if I look for it in the textbook on page 53, it's going to be quite a bit more formal, of course. Okay, actually it wasn't as lengthy. Okay, here it is. The sandwich theorem. Suppose that g of x is less than f of x is less than h of x. F of x is between them. For all x in some open interval containing an x value of c, except possibly x equaling c itself. So you don't really have to know exactly there, because it could be a hole there. Suppose also that the limit of g of x and the limit of h of x are L, then the limit of x of x would also be L. And here's their picture of the red function must be h of x, and the yellow function must be g of x, and then the f of x is the blue. Here it is up here also. The h of x is the red, the g of x is the yellow, and the f is trapped between them, causing their limit to all be equal at this point C. Okay, so it's called the sandwich theorem or the squeeze theorem by trapping f of x between two other functions, forcing their limit to all be the same at a select point. Here is a really interesting example, and don't worry with how complex this stuff may look, because this is really easy to apply. Okay, look at this example 10. Look at these hideous functions. Look at this function, 1 minus x squared over 4 and 1 plus x squared over 2. I guess it's not that bad, but you get a common denominator. This is actually graphed. This red graph is the 1 plus x squared over 2, and the yellow graph is the 1 minus x squared over 4. So they're saying u of x is between them. Given, this is given to you. Okay, you're given that you have some function falling between these two. Find the limit as x is approaching 0, no matter how complicated u is, no matter how ugly this function in the middle is. So how do they do this? Well, they say that the limit of the 1 minus x squared over 4 as x approaches 0 is 1, and the limit of the 1 plus x squared over 2 as x approaches 0 is 1 also. So therefore the u must also be in there. Now let me show you how we can write this a little bit easier. We have 1 minus x squared over 4 less than or equal to u of x less than or equal to 1 plus x squared over 2. The question is, really in the middle, here is the question, what really is the limit of u of x as x is approaching 0? Well, stay with this string inequality or this compound inequality. If I take the limit of the middle, I also take the limit of the left and the right. So go ahead now and write this as the limit of 1 minus x squared over 4 as x is approaching 0, and the limit of 1 plus x squared over 2 as x is approaching 0. So you can write the limits in what they call this string inequality or this compound inequality. So you're just taking the limit of all three. We have no clue what this limit of this function is. We don't even know what the function looks like. We don't know what it algebraically is represented. But we do know that by direct substitution, this value, when you put a 0 in it, 1 minus 0 over 4 is going to be 1. Is that what they got? Okay, is 1. And we know over here by direct substitution, if I put a 0 in, it's 1 plus 0 halves, which is also 1. So that means that whatever this function looked like, it was trapped between these two values. So therefore we claim that the limit of u of x as x approaches 0 must also equal 1 by that squeeze theorem. Okay. So algebraically, I tend to do it a little more structured, a little less wordy, maybe a little more algebraic, and I think, in my opinion, that makes it easier to understand. Okay. Now here's another one, and some of these questions, they look really bad, but if you pay attention to the given information, it's not difficult at all. Did y'all get that? Let me give you just a minute more. Okay. Okay. Maybe I should put on here by the squeeze theorem. don't see how you can see around me. I try to hide behind the monitor. All right. So now let's take a look at another example. Is this 4 after I flip that over and throw it down? Yeah. Okay, I'm taking this one straight from the book, and I'm going to write it down, so don't be concerned. Number 65 on page 56. How's that for a little bit of dyslexia? Okay, given that 1 minus x squared over 6 is less than x sine of x over 2 minus 2 cosine of x, and this is all less than 1. That's pretty ugly. Now the question is, what is the limit as x approaches 0 of x sine x over 2 minus 2 cosine of x? This would not be something fun to have to do. I mean, how would you algebraically manipulate it? I mean, the denominator is 0. Would you want to use tables on this thing? What in the world does the graph look like? You cannot use direct substitution. So this is not a fun thing. But because of what they gave me, I can use this squeeze theorem and say, well, let me take the limit of all 3 parts of this string inequality, which means let's take the limit of the left, the limit as x is approaching 0 of 1 minus x squared over 6, the limit in the middle, which is really the question. What is the limit of that middle function? And then the limit of the constant on the end. Yes? Was it given as less than? What was it? I can see what you're saying, equal to, but I don't think, let me see if it said it. Maybe I copied it wrong. Yeah, I think it would still be okay either way, but, no, it is just a less than. Mm-hmm. They're still trapped in, oh.
Because they all can't be the same, they're all less than each other.
But they're going to be the same at x equals 0. Let's see what happens. They're going to crush them in there, trap it in there, but if you trap it in there, one of them could still have a hole in the graph at that point, and the limit would still be, you know, okay. Right. If there's a hole in the graph, the limit can still exist. So, I saw that. He almost fell. Okay. Okay, right here. Let's do direct substitution. So with direct substitution, if I put a 0 in, it's 1 minus 0 over 6, which is 1. And then the limit of a constant function is still the constant. So here we go. We're trapped between a 1 and a 1. And again, those could be holes in the graph, and it's going to be okay. But if you're trapped in there, so now you can conclude by the Squeeze Theorem or the Sandwich Theorem or whatever, that the limit as x is approaching 0 of x sine of x over 2 minus 2 cosine of x must equal 1. And that, my friends, is the end of this section. But just a real quick, going back to the first page of today's lecture, just thinking about this, find the limit. We can look at a graph. Usually they gave us good graphs, or we can play with them on the calculator to find the limit. We can look at a table of values, and remember you go to that table set and change it so that it's asking for the values rather than automatically calculating them. We can use the limit laws to break the function down so that we're really just taking the limit of a constant or an identity function. We can use direct substitution, but this is seldom a convenient thing because they're going to make them more difficult. We can use algebraic manipulation by factoring and canceling or using the conjugate of a binomial and factoring. And then last but not least, we can use the Squeeze Theorem. So that's just a verbal overview. Now, we're also not quite through for the day, but I'm going to close out this recording, this very lengthy recording.